The Thermal Energy Storage, or TESS experiments, will fly aboard the Space Shuttle Columbia as part of NASA's Office of Aeronautics and Space Technology 2 carrier during the STS-62 mission. Engineers at the NASA Lewis Research Center are conducting materials research that will lead to the development of the next generation of power systems for future spacecraft. Fluoride salts have been selected as test material mainly because they melt and freeze at the high temperatures required for effective use in a space-based power system. However, a primary concern with fluorides is the change in volume, as much as 30%, when the test material is melted. This change in volume produces a void or bubble when the material freezes. How these voids behave under microgravity is not entirely understood.
Suppose that when the salt freezes and contracts at zero gravity, the void all forms near the surface of the container. As we move from shade to sunlight, there is no salt to conduct the heat away from the container's surface. At this point, the container may be subjected to temperatures high enough to burn a hole. On the other hand, what happens if the void forms near the center of the container, away from the surface? Since the salts nearest the surface will melt first, will there be enough room in the container to allow for the expansion of the salts from solid to liquid? If not, the containers may be distorted, again hampering the entire system.
Oak Ridge National Laboratory in Tennessee has developed a three-dimensional program to describe in-space void behavior in fluoride salts. The program is named NORVEX.
The NORVEX code predictions for lithium fluoride salt behavior in space must be verified with data. Such data at the present time does not exist. The test experiments have been developed to provide the low-gravity data needed to verify the NORVEX code. A validated NORVEX code will help lead to future solar dynamic power systems with higher efficiency, longer life, and reduced weight.
Two separate test experiments will fly aboard Columbia. They are identical except for the composition of the fluoride salts. The experiment section has a cylindrical canister charged with the test material. A two-zone heater surrounds the canister. The fluoride salts are melted here on Earth and allowed to solidify with the canister in a horizontal position. This causes a void to be located along the canister wall at a position which is opposite the high temperature zone of the heater. In the microgravity environment of space, the test material will be subjected to 4 melt-freeze cycles. The acquired on-orbit data, along with post-flight data, will determine the extent of the void movement toward the high-temperature heater zone. The data will validate analytical predictions from the NORVEX code. The verified code will help lead to improved heat receiver designs for future solar dynamic power systems. The thermal energy storage experiments are the first time these materials will be tested under extended microgravity conditions. The acquired data is needed to verify analytical predictions for test material behavior. These test experiments will point the way toward a reliable, efficient, and low-cost solar dynamic power system for Earth-orbiting spacecraft.